Hello everybody, we've got a couple of really fun problems today. These are word problems, and word problems are often the bane of students' existence. They don't like them, they don't like doing them, and so I'm excited to go over them to show you it's not as scary as you think it is. You can pause and you can read this on your own, but I'm going to quickly skim through and highlight the things that are important. So we have here, there's a 12-volt battery, we know that. There's a bulb. It's just talking about how it breaks. We have a single bulb with a resistance of 6 ohms. It's connected in series when the flasher is closed. So it looks like from this sentence here and this sentence continues on, we have a flasher that's like a switch. And then we have that a full blink cycle lasts 1 second with the bulb on for 0.4 seconds and off for 0.6 seconds. So this is a really long word problem. You can see though that I've highlighted some important things and it's actually not a whole lot of information. And you'll see that when we draw it. So part one, or question one, it says to draw a simple circuit diagram representing the system when the flasher is closed. Battery, bulb, and flasher switch. So we've got our battery here. Say this is the positive node. I'm going to say it doesn't really matter how you choose to draw it since they're connected in series. And if you read the problem, the only thing we have is the switch, which I've drawn right here. Remember, it says to label it when the flasher is closed. And then the battery, bulb, and switch. So even if you had like bulb before switch, that's totally fine too. It would still be a working system. I'm going to choose though to put our bulb over here. And that's it. So we have bulb, battery, and right here we have our switch. Okay, so that is question one already done. And you can already see that even though this word problem is really long and has a lot of information in it, it's a relatively simple circuit. So now it asks us to calculate the current flowing through the bulb when the flasher is closed. Something I like to do is I like to label the things that we have. So we know that we have our resistance equals 6 ohms. I highlighted that up above. And we have V, our voltage, equals 12 volts. And now you can see, oh, okay, well, I have resistance, I have voltage. I can use Ohm's law and rearrange it. So we know that I equals V over R, and this is just from Ohm's law. So we have I equals 12 over 6. So I equals 12 divided by 6 is 2 amps of current flowing through the bulb when the flasher is closed. So now it wants the instantaneous power consumed by the bulb when it is on. So first thing I like to do is I like to write down the equation for power given the things that I have. From question 2, I now have voltage and current and resistance. So I can really use any of the equations for power. I'm just going to use the most simple one, which is P equals IV. So plugging in our values, we have P equals 2, that's our 2 amps from our current, times 12, that's our 12 volts from our battery. So we have P equals 2 times 12 is 24. And then this is power, so that's watts. Okay, so question 4 now. It asks us to calculate the energy consumed by the bulb during 1 full blink cycle. You'll remember that energy is equal to power times the time that the bulb is on. So we go back to what the values we have. We know that our power is 24 watts. I'm going to write that up here. 24 watts. And then the time that the bulb is on is right here, and it is on for 0.4 seconds. So 24 and then T on equals 0.4 seconds. So our energy is then 24 times 0.4, and this equals, let me calculate it, 9.6. And then this is energy, so we have units of joules. So question 5 asks us, find the average power consumed by the turn signal circuit over the 1 second cycle. So power average is going to equal the energy times the time of the cycle, like the total time that the cycle takes. And the time that the cycle takes is 1 second for a full cycle. So we already have energy is 9.6 joules, and then that's times 1 second. So the average power is 9.6 watts. This isn't the only way that you can solve this, though. You can also solve it using the equation power times time on divided by the time of the cycle. And this would essentially just give you kind of like a power per like the amount of time that it is on. And we already have our power, which is 24 watts, times time on, which is 0.4, divided by 1 second. Let me calculate that. And we find that it is exactly the same, of 9.6 watts. So that's our average power over the 1 second cycle. Question 6 says, suppose the driver leaves the turn signal on for 30 seconds, highlight that, while waiting at a red light. How much total energy, so that's what we want, is consumed by the bulb during this time? So this is another pretty simple equation where we're going to say we want the total energy, and it is going to equal to the energy consumed during one cycle times the number of cycles. So N cycle. So we already found energy during one full blink cycle up here in question 4. And we know that one full blink cycle is it's 1 second. So in 30 seconds, we have 30 cycles. So we have E, which is we found to be 9.6 joules times 30 seconds equals, let me calculate that, 288 joules. And this is just our total energy, this is not seconds. This is just a number. Otherwise, our units wouldn't match up. But it consumes a total of 288 joules over the whole 30-second period. Okay, so we have problem 2 now where things get switched up a little. We're now worried about using solid-state electronics rather than the old thermal flashers. Again, I'll let you pause and read through this, but I'm going to go ahead and underline some important things. It looks like for this problem, we already have them kind of bullet pointed out, so that's helpful. We've got a 12-point battery. We've got an RC current with resistor equals 150 kiloohms and a capacitor of 4.7 microfarads. This signal switches a MOSFET on and off. It controls a LED array. Total resistance equals 24 ohms when on. So the first question asks us, it says the period of an RC circuit is given by the formula T equals 1.4 times tau. And then it asks for the frequency of the blinking signal produced by the RC timing circuit. So the first thing we need to solve from this is this equation here. And tau is something you should write on your note sheets, but tau is equal to resistance times capacitance. So in our case, our resistance is 150 kiloohms or 150,000 ohms, and our capacitance is 4.7 times 10 to the negative 6 farads, because this is microfarads. So we have tau equals 150,000 times 4.7 times 10 to the negative 6. And then remember, this whole thing is multiplied by 1.4 to give us our period. So we're going to do this, and then times 1.4, and that equals our period t. I've already plugged this into the calculator, and we get our period equals 0.99 seconds. So now we have our period. If you recall the relationship between period and frequency is what we want. Frequency equals 1 over the period t. So in our case, this is 1 over 0.99, and period has to be in seconds. That's important to remember. So we get that our frequency is equal to 1.01, and then this is hertz. Okay, next question says, what is the duration of the on time per cycle? So there's a few things I haven't underlined here that are important to solve this problem. And that is located in this sentence here. This is why I always recommend double reading your problems. So we have the RC timing circuit creates a square wave with equal time spent at its high and low values. So I'm going to underline that. That essentially means that it has an equal amount of time spent on as it does off. So we know that the period is the time of the whole circuit. So like the amount of time that the circuit is on, or how long it takes for a cycle to complete. So if we know that the period is the amount of time the cycle completes, let me actually draw a graph for this. So it says it creates a square wave. I'm going to say that like this is off, this is on. So it has an amount of time off, and then it jumps up to on, and then it has the same amount of time off, and then the same amount of time on. And it goes like that for as long as it's on. And then one period is this amount of time here. So if the distance here is equal to the distance here, then we know that if we're interested in just the on cycle here, it is the period divided by 2, since these are equal. So we have the time on equals period t divided by 2. We already have our period is, let's see, it's 0.99 seconds. It's divided by 2. Plug that into the calculator. That is roughly 0.495 seconds. Okay, so question 3 asks us to calculate the current through the LED array when the MOSFET is on. So going back to our initial problem, the things that I think about for current are voltage and resistance. We have voltage here, and we have our resistance defined here. So I'm going to write voltage equals 12 volts. Looks like a U. Volts, and resistance equals 24 ohms. Yep. And then the reason that I'm using our 24 ohms instead of our 150 kiloohms here is because it's interested in the LED array. And the 24 ohms for bullet point 3 is what happens when the LED array is turned on. So using, again, Ohm's law, I equals V over R, we have, this is going to be 12 over 24. So we have 0.5 amps when the circuit is closed. This is how much current is through the LED array. So now it asks us to determine the instantaneous power consumed by the LED array while it is on. So we're still just interested in the array. We can use the same equation that we used earlier, which was power equals current times voltage. We already have our current, it's 0.5. We already have our voltage is 12. So this becomes 0.5 times 12, which is 6 watts. Question 5 says calculate the average power consumed by the LED array over one full blink cycle. So key pieces of information here. We know that one full blink cycle is 0.99 seconds. And we know that the time that the blink cycle is on, we calculated it earlier, is 0.495 seconds. So we have T on equals 0.495, and then T cycle equals 0.99. And then we have our power, which we calculated up above, is 6 watts. And we'll use the same equation we used earlier, where power average equals power times time on divided by the time of the cycle. And you'll notice with this equation that this has units of seconds, this has units of seconds. So the 2 seconds cancel each other out, and we're left with average power has the same units as power, which is exactly what we want. So when we calculate that out, we have 6 watts times 0.495 over 0.99. And this equals, oh, that's nice. It equals exactly 3 watts. Okay, last question. We have, suppose the driver leaves the turn signal on for 30 seconds while waiting at a red light. How much total energy, also we have 30 seconds here, is consumed by the bulb during this time? And then you can think about how this compares to the older turn signal control. So the equation for total energy, E total, equals average power times the time that a cycle takes times the number of cycles. So we have average power we already found is 3 watts. Time that a cycle takes we already found is 0.99 seconds. These are multiplied together. And then for the number of cycles, the way that you would do this is you would do 30 divided by 0.99 seconds. So let me do that real quick. 30 divided by 0.99 is 30.30. And then this repeats on forever. So I'm going to do an estimation here and say that the number of cycles is roughly 30. And then we'll get an approximation. But this is okay because we're really worried about how this compares to the older turn signal control. And we'll still get a pretty accurate, we're accurate within a decimal point or two. So when we do 3 times 0.99 times 30, calculating that out is we get 3 times 0.99 times 30. This is 89.1 joules. So this is significantly less than the older thermal turn signal control, our older one, let's go back to it, was 288 joules. Whereas this one is only 89.1 joules. So the new system is much more efficient than the old system, which is very nice. And probably why it's the new system and the one more widely used today. We're all about energy efficiency. Okay, so that's 2 word problems solved. I hope you guys not only enjoyed this video, but I hope it showed you that word problems are not as scary as you think they are. As long as you break it down, I always suggest highlighting it. I always suggest writing out the equations that you know that you have, whether that be on like a cheat sheet if you get it on your exam, or maybe you have to memorize them. But if you underline things and you really read through it a couple of times, you'll see, okay, word problems are not as scary as you think they are. They're actually one of my favorite problems to solve because they're normally, once you understand it, it's normally not as hard as if they just gave you a bunch of numbers and you had to do the algebra to figure it out. But as always, good luck.